Okay, calculus, let's do 13.5. It's the chain rule for several variables. Now, you've seen chain rule before in Cal 1 and applied it ever since then. It's a little bit different, but not too difficult. It just involves multiple derivatives with respect to t. So if w is a function of x and y, and f is differentiable with respect to x and y, where x is some function in terms of time, as is y, where g and h are also differentiable in terms of time, and w is a differentiable function with respect to t, and the derivative of w with respect to t is dw dx times dx dt plus dw dy times dy dt. Now, the easiest way to kind of see what's happening here is through an example. So we have w equals x squared y minus y squared, and we have x equals sine t and y equals e to the tth power. Find dw dt when t is 0. So let's find dw dx. Derivative of w with respect to x is 2xy. This is a constant. The derivative of w with respect to y is x squared minus 2y. Now we also apparently need the derivative of x and y with respect to time, so let's do dx dt. Derivative of sine t is cosine t, and dy dt. Derivative of e to the t is just e to the t. Now it says dw dt is equal to dw dx times dx dt, so that's 2xy cosine t plus x squared minus 2y times e to the t, dw dy times dy dt, but we should be able to convert our x and y respectively into terms of t because we want this with respect to t. So we know x is sine t and y is e to the t. So this is 2 e to the t sine t cosine t for y and x. X squared minus 2y becomes plus, looks like sine squared t minus 2 e to the t all times e to the t. If we distribute on that second part, we've got 2 e to the t sine t cosine t plus sine squared, or e to the t sine squared t minus 2e to the 2t. Now, if you thought, well, why couldn't I have just subbed in sine of t and e to the t originally and just taken the derivative there? You can, and it would be the same thing. So if you want to check it, you're more than welcome to. Theorem 13.7, chain rule with two independent variables. If w is the function of x, y, where f is differentiable, if x is a function of s and t, and y is a function of s and t, so basically this is two variables and then two variables, such that the first partials, dx ds, dx dt, dy ds, and dy dt all exist. Oh, by the way, we're supposed to plug this in at 0. We'll go back and do that in a second. Then dw ds is a partial you have, and dw dt is also a partial you have, using the same strategies. Now, it says I was supposed to plug this in at t equals 0. Sine of 0 is 0, so these are all going to become 0. This last one, though, e to the 0th is 1, so this should be negative 2 if we're plugging in 0. I forgot about that part, but not a big deal. So let's figure out what this is talking about in the next problem, next page. We have a word problem to do before we get to two variables, though. Two objects are traveling in elliptical paths by following the parametric equations below. At what rate is the distance between the two objects changing when t equals pi? So we need to find dw dt for both set of points and the relative values. So we know for the first point, we should have dw dx1 times dx1 dt plus dw dx, or dy1 times dy1 dt is the first one, equals dw dt, I'm going to call this 1. And the same thing for 2, dw dx2 times dx2 dt plus dw dy2 times dy2 dt is dw dt2. Okay, so now, seeing this, I'm going to have to find the derivative of this. And what function are we talking about in terms of w? Well, w is the distance formula because it wants the distance between the 2 points, or the rate of change. It's the derivative of the distance formula more appropriately. So if w is the square root of x2 minus x1 squared plus y2 minus y1 squared, the derivative of this is going to be different for each of these depending on the variable. So it'll change things a little bit. Furthermore, I'm going to need all of these things, the derivatives with respect to time. So I'm going to write those out here. So dx1 dt, derivative of 4 cosine t is negative 4 sine t. It's at pi though, so t is 0. So we know dx1 dt is 0, which means I don't have to do this derivative because it's 0. dy1 dt is 2 cosine t. At pi, that's negative 2. dx2 dt is the derivative of 2 sine 2t becomes 4 cosine 2t, which should be 4, because cosine of 2 pi is 1. And then dy2 dt, the derivative of 3 cosine 2t should be negative 6 sine 2t, which is 0. So I know dy2 dt is 0 as well. What that means is I don't need to do either of these two. I only need to do these two. So, and we know what those values are. So what is dw dy1? It's the derivative of this with respect to y1. So that's going to be 1/2 times x2 minus x1 squared plus y2 minus y1 squared, all to the negative 1/2 times the derivative of the inside with respect to y1. The derivative of the inside with respect to y1 will be, should be 2 times y2 minus y1. Really negative though, because there's a negative in front, so chain rule on the inside, so negative 2 times y2 minus y1, which in total, the negative 2 and the 1/2 will just become negative. And the negative can switch the order here, so it'll be y1 minus y2 over the square root of x2 minus x1 squared plus y2 minus y1 squared. And all of that will end up being multiplied by this number here. What is y1 minus y2 at, if we plug these all in at pi, looking at our equation, y1 at pi is 0, y2 at pi is 3, so it should be, looks like negative 3. And this distance formula is conveniently 5 if you plug it in here. So this is negative 3/5 times the negative 2, which is 6/5. If we do the same thing with, now with the only other one we need is dw dx2, it's exactly the same derivative-wise. It's x2 minus x1 over the same square root, x squared minus x1 squared, plus y2 minus y1 squared. Now x2 minus x1 in this case ends up being 0 minus negative 4, so it's positive 4 divided by 5 times the 4, which is 16/5. So these are the two things that are added together to show the differences in distances, so it's just 6/5 plus 16/5, which is 22/5. And we'll finish this section in the next video.